We've been considering 2x2 linear systems, so systems that have the following form. If we want, we can put it in standard form to more clearly understand what the system looks like. And in particular, we've been talking about trying to find trajectories in the phase plane. And the equation by which to do that turns out to be a first-order nonlinear equation. So if we plug in the specific expressions for x prime of t and y prime of t, we'll get this. Now, the unfortunate thing here is that this is not separable, at least not the way it looks. So that gets us to ask the natural question, how do we solve this? Now, it turns out that a substitution is going to help us. Now, generally with substitutions like this, if we can write our dE like this, y prime of x is some function of y over x, then the substitution u, y of x over x, will convert this into a separable dE. So that's great. If we can do this, then we'll be able to solve it using the techniques we've talked about before. So here's an example of a system. Now this, again, 2x2 system. We can show that the eigenvalues of this system will be -1 plus or minus root I. So this should provide us with a stable spiral as our phase portrait. Now the equation for the trajectories, we're going to have y prime of x. Y prime of t is the bottom equation here. So that's going to give us negative x of t, negative y, divided by x prime of t. So that's going to be negative x plus y. So really, when we're solving these trajectory equations, we don't need to explicitly see the t dependence. That's not what we want. Now here's where the substitution part comes in. We're going to take this. We are going to factor out, in this case, a negative x. This will give us 1 plus y over x. And if we take out another negative x, we'll get a 1 minus y over x. Now, of course, note x won't be allowed to be 0 in this particular situation, and that's fine. Those negative x's will cancel out. And we've succeeded in writing this expression for the dE, this nonlinear first-order dE, we've succeeded in writing it as a function of y over x. So now it's time for our substitution. So we are going to let u of x be y of x over x. And that means we could reorganize things and have y of x equal to x times u. We are going to try to replace this entire dE in terms of u and x. So obviously we'll need to replace y prime. We'll use the product rule. We'll get u of x plus x times u prime of x. And then we're going to substitute this in. So when we substitute this in, we'll get just that. We'll get x times u prime plus u, 1 plus u over 1 minus u. We'll get x times u prime, 1 plus u over 1 minus u, subtract u. And if we put all of that over a common denominator, what we're going to see is that we'll end up, these terms will cancel, we will end up with a nice expression. And now it's a little bit more clear that this is in fact separable. We'll have some expression for u multiplied with this expression for x. So yes, this substitution works. And that's great. So now we go ahead and we separate, we solve. We'll bring all the terms with u together on the same side of the equation as the u prime. We'll have our 1 over x. Remember that we are anti-differentiating with respect to the same variable on both sides with respect to x here. This is effectively running the chain rule in reverse. This will give us a new variable, a new integration variable. We'll get the following there. And now, on this side, we'll get this. This can be dealt with fairly straightforwardly. 1 over 1 plus u squared du, subtract u over 1 plus u squared du, natural log of x plus c. This first expression here is just an inverse tan, so we'll have an inverse tan of u. This second expression, what we'll need to do is substitution, a different substitution. We will let u, or 1 plus u, equal w. 1 plus u squared. dw will be 2u du. So in this particular situation, insert a page here. So in this situation, what we'll get is the following. Get a mess here. I'm just losing some of my pages. So at this point, I'll insert page. Sorry, folks, technical difficulties here. I'm just going to jump right to it. We will have tan inverse of u, subtract 1/2 dw over w, natural log of x plus a constant, tan inverse u minus 1/2 natural log of w, natural log of x. Now we begin the substitution process again. Tan inverse of u minus 1/2 natural log of 1 plus u squared. And we can continue to massage this expression down. Remember, we didn't start this problem with u. We started it with x's and y's. So if we continue to resubstitute, we'll end up with the following. Natural log square root of 1 plus y over x. Remember that a number in the front of the natural log gets to be absorbed as a power. In this expression right here, I'm going to write this as natural log of square root of 1 over x squared, and that's going to give me an x squared plus y squared. That is going to give me a natural log 1 over x, natural log x squared plus y squared, which I could then write as negative, this is, sorry, a product on the inside of the logarithms. I have to be a little bit more careful. This I could write then as a sum, or in this case, a difference of these two logarithms. And that will give me natural log of x plus natural log, or in this case, we'll separate it out there. Natural log x squared plus y squared. So, tan inverse y over x, this is going to add up because there's a negative sign in front of this whole expression, minus this natural log of x plus a constant. Those terms will cancel out, and we will end up with tan inverse of u of y over x minus this stuff equals c. Now this turns out to be some function of both x and y, so this is what we call our implicit solution. We don't solve for y in terms of x. Can't do it, too complicated. Now, that's sometimes it might feel like it's a bit of a letdown, but what you can actually do is take this and use Maple, for example, and you can go in Maple and do something called Implicit Plot. And within Implicit Plot in Maple, you can choose different C values and use an implicit plot. And then you can overlay that implicit plot on the slope field. Now, as you saw earlier when I had technical difficulties, if we go back to this picture, this is in fact the slope field for our differential equation. We can see that 0, 0 is in fact the stable spiral. And what I've plotted here are the trajectory curves. So that expression that we got, those were the trajectory curves, and I overlaid them on this plot. As always, when we do this, we are eliminating the parameter, and we can't get a sense of direction. But thankfully, we have the slope field, and we can see that the implicit solution does line up with the DE, with the slope field. And so that's both satisfying and unsatisfying at once. It's great that we can actually do some math and get some expressions for the trajectory curves, but they only tell us a limited amount. The formulas have to be functions, so they have to pass the vertical line test. We might have to overlay several branches of these curves. Nonetheless, this is a useful technique, especially when it comes to finding trajectories.